Hello everyone and welcome to another video. Today we will be tackling the path sum problem on LeetCode. The path sum problem involves binary trees and it also involves recursive algorithms. So here's the problem. Given a binary tree and a sum, determine if the tree has a root to leaf path such that adding up all the values along the path equals the given sum. So we're given an example here. We have a binary tree and we want a sum of 22. Luckily, they give us the answer here of a valid path, which is 5, 4, 11, 2. This corresponds to here, 5, 4, 11, 2 in our tree. And if you add them all up, if you add these numbers up, you will get the sum of 22, thus making it a valid path from root to leaf. That's why in this example here, we have to return true. If no such path were to exist, that's when we would return false. So let's have a look at our structure here. And I'm going to reset my code because we'll be coding it again later on in the video. But looking at the structure, we have a tree node which defines a value and also a left and right child. If there's no left or right child, it's called a null pointer. So as our function, we're going to be given a root and we're going to be given a sum, which you'll be aiming to get. Okay, so how might we approach a problem like this? Well, a lot of the time with binary trees, we want to look at recursive algorithms that allow us to do this problem. What is a recursive algorithm? Well, a recursive algorithm, you can think of it like a function that needs to solve a problem. And so that function will call itself to solve that problem, if that makes sense. So the most common example is the Fibonacci sequence. To find the nth Fibonacci number, you will call the function again on n-1 and n-2 to find the n-1 and n-2 Fibonacci number before you can calculate the nth Fibonacci number by adding the two together. Okay, so how do we apply this recursive algorithm idea to a problem like this on a binary tree? Well, the idea always comes by trying to break our problem into sub-problems that we can maybe apply to different parts of our tree to get the answer. Now, by definition, binary trees are sort of a recursively defined structure. Why do I say that? It's because binary trees are made up of a bunch of subtrees. So for example, looking at this one here, we can see that 7 is a subtree, 2 is a subtree, 1 is a subtree, and then 11 connects two subtrees together. 4 connects, this 4 node here connects one subtree to its left side, and 5 connects two more subtrees together. So you can see there's this constant repetition of subtrees that form up the structure of our binary tree. And we can take advantage of that in our recursive algorithm to try and find the path sum solution. Okay, now we've established that. What can we do to try to make our problem fit this? Well, as I said, we need to find subproblems, and one particular subproblem might be noticing that if there were to exist a path from our root node to the bottom of length 22, then there would also exist paths on nodes that are the children of 5 that also go to the leaf node and have a particular sum. Let me clarify. So here, 5, as we know from the example, has a path from itself to a leaf node of 2. In particular, this path is on the left-hand side. There's no path on the right side that also satisfies the property of sum equals 22. So, if we know that 5 has this path of sum 22 to the leaf, then we also know that this node 4 has a path to its leaf of sum 22 minus 5, or 17. This is where the recursive algorithm comes in, because you see, we've essentially repeated the problem only on a subtree of the tree. So before we were asking if there was a path to the bottom, length 22 from 5. Now we're asking if there's a path to the bottom, length 17 from 4. In this case, we've sort of reduced the problem into a smaller, easier to manage sub-problem. And we can sort of keep doing that as we keep going down the tree. So 4, we can again break it into a sub-problem. So you can ask 11 whether there is a path of length 17 minus 4, which is 13, to a leaf. And then eventually we can get to a leaf here, maybe 2, and that's when we can ask, okay, well, is there a path from yourself to a leaf that is of length 2? Now, once you're at a leaf, it becomes very clear whether there doesn't exist a path or not. Because, well, there's only one possible path from a leaf to a leaf, right? Which is itself. That means that we can simply check the value of our leaf and compare it to the sum that we want. And if they are the same thing, then we can return true back to our node 11 here. Node 11 would say, okay, there is a path down to node 2, a valid path that is, and it will come back to node 4, and so on, and return true to node 4, and then return true to node 5. So what we just described here, this breaking down into sub-problems, is what we call our recursive step. Just like in Fibonacci, how we need the n-1th and n-2 Fibonacci numbers to make the nth Fibonacci number, in here we need the solution for our child 4 and our child 8 in order to generate the solution for our child 5. Namely, is there a path from 4 to a leaf of length 17? Or is there a path of 8 to a leaf of length 17? And if any of those paths exist, then there is a path of length 22 from 5. If none of them exist, then there is no path from 5 to a leaf length 22. Okay, so that's our recursive step. Now we need to look into something that's called a base case. The base case is essentially what allows our recursive algorithm to stop. It's a sort of condition that once met, we can very easily calculate the answer to the subproblem. So it's like a subproblem that's so easy that it is trivial to calculate. So we've already actually sort of encountered this already when we reached the leaf node. When we were at 2 here, it became trivially clear how to calculate whether there was a path of length 2 starting from 2 and ending at a leaf node of length 2. And it was obtained just by comparing the value of 2 as well as the desired target. The same thing could have been said of 7. Once we reach the leaf node of 7, if we were to ever reach here, well, then we can easily check whether there's a path from 7 to a leaf, i.e. itself, of some length 2, in which case there isn't. So that is what we consider our base case, a subproblem so easy that it's trivial to solve. Going back to our Fibonacci example, you could imagine that our base case would be when n equals 1 and when n equals 2. Because we know for a fact that the first two numbers of Fibonacci are just 1 and 1. And we can use that to sort of build up and get the answer to every other part of the Fibonacci sequence. Okay, now that we've established a base case and a recursive step for our algorithm, let's try and go through an example here just to see how it works, just to clarify. So looking at 5 here, we want to know if there is a path length 22 from 5 to a leaf. So first thing we need to do is we need to check the base case. Is 5 a base case? Well, in this case it's not, because 5 is not a leaf. So we'll check its children now. So we'll start at node 4 arbitrarily. We can go with node 8 first if we want, but it does not matter. And we can see that the time complexity at the end will remain the same no matter what. But for the sake of argument, let's say we're going to node 4. Node 4, we once again check if it's a base case. It's not a leaf, so it's not. And then we can ask if we can go to another node, which is a child of node 4. So when we went from 5 to 4, the sum we wanted decreased from 22 to 22 minus 5, which was 17. Now node 4 will ask 11 whether there is a path of length 17 minus 4, which is 13, from 11 to a leaf. Now 11 here, we check the base case again, as always. 11 is not a leaf node, so we need to ask its children. So we go to 7. 13 minus 11 is 2, so we ask 7 whether there is a path of length 2 from 7 to a leaf. Now we finally have reached the base case, because 7 doesn't actually have a child. So in this case, what we can do is we can simply compare the value of 7 to the desired sum. 7 doesn't equal 2, so 7 returns false. There's no way we can make a path from root going through 7, or in other words ending at 7, because 7 is a leaf, such that there is a path sum of 22. So 7 will return false. 11 sees that there's no path on the left hand side, so now it checks the right hand side. So 11 will check 2, and it will say, okay 2, is there a path from you to a leaf node that is of length 2? Our base case condition is met now because 2 is a leaf node. And of course, we can actually see that the value of 2 is equal to our desired sum. So there does exist a path through 2 to 2 that has a path sum of 2. That's a lot of 2's. Anyway, 2 will return true because it has found it. 11 will see that there is a path on the right hand side, so it will also return true. 4 will see that there's a path through 11, so it will also return true. And finally, 5 will also return true because it sees that there is a path through 4. So in that way, we've sort of gone down the tree until we've reached a sort of base case where we've noticed that there is a valid path, and we've sort of gone back up the tree again and told 5, yes, there does exist a path. For the sake of argument, now let's consider what would happen if there did not exist such a path. So maybe perhaps consider if this 2 were replaced by a 3. Well, then it wouldn't be hard to imagine that our algorithm will go through the entire tree trying to look for a valid path. Each time it reaches a leaf node, the base case condition will be met, but there won't be a valid path from itself to a leaf node that has the desired sum. So it will always return false at the leaves. And then eventually, as every single node returns false and we keep going back up the tree, node 5 would say, okay, well, I've asked 4 and there's no valid path there. And I've asked 8 and there's no valid path there. Therefore, there's no valid path from 5 to a leaf node that is of sum 22. In that case, 5 will return false. And we can see that our algorithm works. So let's have a look at the complexity now. We need to consider what is the running time of this algorithm. So we know that with this recursive algorithm we have, that we visit every single node exactly once. Once we visit 5, we'll ask 4 and 8. And then once we get that result, we do go back to 5, and we do some constant time operation, and then we return. So for every node, we do constant time operations, and we also know that we visit them once only. So we know that this algorithm is order n, where n is the number of nodes in the tree. Okay, so hopefully after the explanation and the example, you've got a good idea of how this algorithm works. Now let's go on to the coding part. So this is our function that we briefly went over at the beginning. Now we have to consider our base case and recursive step. The first part of actually coding it is the recursive step, the base case. So in this case, there's sort of 2 base cases that apply here. The first one is what happens if root is a null pointer. In other words, what happens if the tree is an empty tree? There is not a single node there. I'll write a quick if statement to handle that. And if there is no root, there is no null point, there is no tree, then there can't possibly exist a path of any sum, right? Because there's no nodes that can actually make up the path. So here we'll just do a simple return false. As for my notation here, you might be wondering why I can use a not root here. Well, in C++, the null pointer, as we know, is the 0 value. It is represented by 0 in memory. So this, what it's just doing, is it's checking that if root equals null pointer, we return false. Null pointer equals 0, so we can replace it. It looks something like this. And since the if statement will return, how should I put it? The integer here will return true if it's positive and false if it's negative. That's why we can use this just not notation here to represent whether root is a null pointer or not. So let's move on to our other base case here, which as we said is if the root is a leaf node. So here we already know that root is not a null pointer, which means that we can actually are free to access the properties of root without worrying whether it actually is a node or a null pointer. So to check if it's a child, it must not have any children. So I will use the notation that I described before in the same way to check whether root has children. If it does not have children, that means our base case is met, and we want to compare the value of root to the desired sum of the function. So all we have to do is do a simple equality check. If our root's value is equal to the sum, we return true. If our root value is not equal to the sum, then we return false. Next, we move on to our recursive step. So remember, our recursive step was to look at the left child and see whether there was a valid path of sum minus root value, and then check the right child to see if there was a valid path of root minus sum minus root value. If there was a path on the left, then we return true. If there's a path on the right, then we return true. But if there are no paths on either side, that's when we return false, i.e. there's no valid path from this node to a leaf that satisfies the sum condition. So let's write that. So since it's a recursive algorithm, we need to call our own function again. Here we'll call it on our left child with a sum of sum minus root value. If this is true, then we return true. Otherwise, now we're going to query the right-hand side. So once again, we'll recall our own function. That's what the recursion part is all about. On the right child of the root, and we'll have the same sum value here. And if that returns true, then we can return true here as well. Finally, if none of these if statements return true, then we can return false at the end and say that there is no valid path through this root node. Okay, so looking at this algorithm, it seems to be right, so I'm going to try and submit it. And it got accepted, which is perfect. So hopefully, after this explanation and code tutorial, I hope you found this video very useful. I would recommend that you try to code this problem yourself on LeetCode. It is called path sum. And I also recommend that you try some of the other recursive algorithm problems in the binary tree section of LeetCode. Other than that, I hope you enjoyed my video, and I will see you next time.